Hello there, and welcome to the Sleepy Science Society. Tonight, we're drifting into the endless dance of weather, that magnificent performance happening all around us, every moment of every day. If you find comfort in these quiet journeys through science, I gently invite you to like this video and subscribe to the channel. It helps others discover this peaceful corner where curiosity meets calm. But for now, all you need to do is settle in, let your shoulders drop, and allow your mind to float upward into the atmosphere itself. Weather is the poetry of physics written across the sky. It is the warmth of sunlight on your face, the gentle patter of rain against windows, the crisp bite of winter air, and the electric charge that fills the atmosphere before a storm. Weather shapes our days, influences our moods, and connects us to the fundamental forces that govern our planet. It is both ordinary and extraordinary, familiar yet endlessly surprising. As you relax tonight, imagine the atmosphere not as empty space, but as an ocean of air, constantly moving, constantly changing, responding to forces both visible and invisible. This ocean extends upward from the ground beneath your feet to the edge of space itself, and within it, countless processes unfold simultaneously, each one contributing to the weather you experience. Let your breathing slow as we begin to explore this atmospheric realm. The science of weather is called meteorology, and it represents one of humanity's oldest attempts to understand the natural world. For thousands of years, people have looked to the sky, searching for patterns, seeking to predict what comes next. Tonight, we'll follow that same curiosity, but gently, allowing each concept to settle like snow, one delicate piece at a time. The foundation, Earth's atmospheric embrace. The atmosphere surrounds our planet like an invisible shield, extending roughly 100 to 125 kilometers above the surface. This may sound vast, but if Earth were the size of an apple, the atmosphere would be no thicker than the apple's skin. Yet, within this delicate layer, all weather happens, all life depends on its presence, and countless processes work together in intricate harmony. The atmosphere is not uniform. It exists in distinct layers, each with its own characteristics and role. The lowest layer, where we live and where weather occurs, is called the troposphere. This layer extends from the ground to about 10 kilometers high at the poles and up to 18 kilometers at the equator. Here, air temperature generally decreases as you climb higher, dropping about 6.5 degrees Celsius for every kilometer of altitude. The troposphere contains roughly 80% of the atmosphere's total mass and nearly all of its water vapor. Above the troposphere lies the stratosphere, home to the ozone layer that protects life from harmful ultraviolet radiation. Still higher, the mesosphere, thermosphere, and exosphere stretch toward the vacuum of space. But weather, the subject of tonight's exploration, confines itself almost entirely to that bottom layer, the troposphere, where the air is thick enough to support the complex interactions between heat, moisture, and motion. The atmosphere is a mixture of gases, primarily nitrogen, making up about 78%, and oxygen at 21%. The remaining 1% includes argon, carbon dioxide, and trace amounts of other gases. But there is another component. invisible yet crucial: water vapor. The amount of water vapor in the air varies dramatically from place to place and time to time, ranging from nearly zero in desert air to about 4% in humid tropical regions. This water vapor, despite being a small fraction of the total atmosphere, drives much of the weather we experience. Everything begins with the sun. Our star pours energy onto Earth's surface, about 1,366 watts per square meter at the top of the atmosphere. This energy arrives as electromagnetic radiation, primarily visible light and infrared heat. When this radiation strikes the ground, it warms the surface. The ground then radiates this heat back upward, warming the air above it. This simple process, solar heating of Earth's surface, is the engine that powers all weather. But the heating is uneven. The sun's rays strike the equator more directly than the poles, delivering more energy per square meter near the equator. The tilt of Earth's axis means different parts of the planet receive different amounts of sunlight during different seasons. Oceans, forests, deserts, and ice sheets all absorb and reflect sunlight differently. This uneven heating creates temperature differences across the planet's surface, and these temperature differences set the atmosphere in motion. Warm air is less dense than cold air. When a patch of ground heats up during the day, it warms the air directly above it. This warm air becomes lighter, more buoyant, and begins to rise, much like a hot air balloon. As it rises, cooler air from the surrounding areas flows in to replace it, creating wind. This rising and sinking of air driven by temperature differences is called convection, and it is one of the fundamental mechanisms behind weather. As warm air rises, it expands because the atmospheric pressure decreases with altitude. This expansion causes the air to cool, even though no heat is being removed from it. This process, called adiabatic cooling, is crucial for cloud formation and precipitation. Similarly, when air sinks and compresses, it warms through adiabatic heating. These processes of rising, cooling, sinking, and warming create a continuous circulation of air throughout the troposphere. The atmosphere is never still. At any given moment, vast rivers of air flow around the planet, carrying heat from warm regions toward cold ones, transporting moisture from oceans to land, and redistributing energy to maintain a kind of balance. Without this atmospheric circulation, the equator would be unbearably hot, and the poles would be far colder than they already are. Weather, in this sense, is the atmosphere's way of fanning out the sun's unequal heating. Gravity holds the atmosphere in place, preventing it from drifting into space. The weight of all that air creates atmospheric pressure, the force exerted by air molecules pressing down on everything below. At sea level, this pressure averages about 1,013 millibars, or 14.7 pounds per square inch. We don't notice this pressure because our bodies are adapted to it, but it is always there, pressing on us from all directions. Changes in this pressure, as air masses move and weather systems develop, are key indicators of changing weather conditions. The dance of heat and pressure. Temperature and pressure are the two most fundamental variables in meteorology, and they are intimately connected. Understanding their relationship is essential to understanding weather. Temperature measures the average kinetic energy of air molecules, how fast they are moving and vibrating. Pressure measures the force those molecules exert as they collide with surfaces and with each other. When air warms, its molecules move faster and spread farther apart. The air expands and becomes less dense. A given volume of warm air contains fewer molecules than the same volume of cold air, and therefore weighs less. This lighter, less dense air then creates lower pressure. Conversely, when air cools, its molecules slow down and pack more closely together. The air contracts and becomes denser, creating higher pressure. These pressure differences drive the wind. Air naturally flows from areas of high pressure toward areas of low pressure, much like water flowing downhill. The greater the pressure difference, the stronger the wind. On a weather map, areas of equal pressure are connected by lines called isobars. When isobars are packed closely together, it indicates a large pressure difference over a short distance, and therefore strong winds. When isobars are widely spaced, winds are gentle. High-pressure systems, called anticyclones, form when air aloft cools and sinks. As the air descends, it compresses and warms, which reduces its relative humidity. Sinking air suppresses cloud formation. So, high-pressure systems are generally associated with clear skies and calm weather. In the northern hemisphere, winds flow clockwise around high-pressure systems, while in the southern hemisphere, they flow counterclockwise. Low-pressure systems, called cyclones or depressions, form when air rises. As air ascends, it cools and can no longer hold as much water vapor. The moisture condenses into clouds and often produces precipitation. Rising air must be replaced. So, air from surrounding areas flows inward toward the center of the low-pressure system. In the northern hemisphere, this inflowing air spirals counterclockwise, while in the southern hemisphere, it spirals clockwise. Low-pressure systems bring clouds, precipitation, and generally unsettled weather. The direction of these spirals is determined by the Coriolis effect, a consequence of Earth's rotation. As our planet spins, anything moving across its surface appears to deflect to the right in the northern hemisphere and to the left in the southern hemisphere. This is not because a force pushes the air sideways, but because Earth rotates beneath the moving air. Imagine standing at the North Pole and throwing a ball to someone at the equator. By the time the ball reaches the equator, Earth will have rotated beneath it, and from the thrower's perspective, the ball appears to have curved to the right. The same principle affects moving air, causing it to spiral around pressure systems rather than flowing directly from high to low pressure. The Coriolis effect is zero at the equator and increases toward the poles. This is why hurricanes, which depend on the Coriolis effect to organize their rotation, do not form within about 5 degrees of the equator. It is also why large-scale weather systems in the middle latitudes, like the storms that cross North America and Europe, have such distinct spiral structures visible from satellites. Temperature variations across the globe create semi-permanent pressure systems. Near the equator, intense solar heating causes air to rise persistently, creating a band of low pressure called the Intertropical Convergence Zone. Here, trade winds from the northern and southern hemispheres converge, bringing moisture and producing frequent thunderstorms and heavy rainfall. This is why tropical rainforests thrive near the equator. At about 30 degrees latitude, both north and south. The air that rose at the equator has cooled and sinks back down, creating bands of high pressure called the subtropical highs. These are regions of descending dry air, and many of the world's great deserts, including the Sahara, the Arabian Desert, and the Australian outback, sit beneath these subtropical high-pressure zones. Near the poles, cold temperatures create high-pressure systems, and between these polar highs and the subtropical highs, around 60 degrees latitude, lie the subpolar lows, zones of rising air where warm air from the subtropics meets cold air from the poles. These polar fronts are breeding grounds for the mid-latitude cyclones, the large storm systems that bring changing weather to much of North America, Europe, and Asia. These global patterns of rising and sinking air, combined with Earth's rotation, create the planet's major wind belts. Near the equator, the trade winds blow from the northeast in the northern hemisphere and from the southeast in the southern hemisphere, converging at the Intertropical Convergence Zone. In the middle latitudes, the westerlies blow from the southwest in the northern hemisphere and from the northwest in the southern hemisphere. Near the poles, the polar easterlies blow from the northeast in the northern hemisphere and from the southeast in the southern hemisphere. But the atmosphere is not a simple machine. It is a chaotic system, sensitive to small disturbances that can amplify into large changes. A butterfly flapping its wings in Brazil might not literally cause a tornado in Texas, but the metaphor captures a profound truth about weather. Tiny variations in initial conditions can lead to vastly different outcomes. This is why weather forecasting remains challenging, despite our sophisticated technology and deep understanding of atmospheric physics. The atmosphere's inherent chaos limits our ability to predict weather more than about 2 weeks in advance, and even short-term forecasts carry uncertainty. Temperature and pressure work together to define weather at any given moment and location. A warm, humid day with low pressure might feel heavy and oppressive, the kind of day when thunderstorms threaten. A cold, clear day with high pressure brings crisp, invigorating air. The interplay between these variables, combined with the effects of wind and moisture, creates the infinite variety of weather conditions we experience. Water's journey through the sky. If temperature and pressure are the skeleton of weather, water is its lifeblood. Without water vapor in the atmosphere, there would be no clouds, no rain, no snow, no fog. The sky would be endlessly clear, and weather would be far simpler and far less interesting. Water's ability to change phases, from solid ice to liquid water to gaseous vapor and back again, makes weather dynamic and complex. Water enters the atmosphere through evaporation. When liquid water absorbs enough heat energy, its molecules gain sufficient speed to break free from the liquid surface and enter the air as water vapor. This happens over oceans, lakes, rivers, moist soil, and even from the leaves of plants through transpiration. The warmer the air and the surface, the faster evaporation occurs. This is why hot, dry days can quickly dry out puddles, and why tropical oceans contribute vast amounts of moisture to the atmosphere. The atmosphere can hold only so much water vapor, and this limit depends on temperature. Warm air can hold more water vapor than cold air. This is a crucial concept in meteorology. When air is holding as much water vapor as it can at a given temperature, it is said to be saturated, and its relative humidity is 100%. If the temperature drops while the amount of a water vapor remains constant, the air reaches its saturation point. The temperature at which this happens is called the dew point. When air cools to its dew point, water vapor begins to condense back into liquid droplets. This is how clouds form. Condensation does not happen in perfectly clean air. It requires tiny particles called condensation nuclei to provide surfaces on which water vapor can condense. These particles include dust, salt crystals from sea spray, smoke, particles, and pollen. Fortunately, the atmosphere is full of such particles, so condensation occurs readily when conditions are right. Clouds form when rising air cools to its dew point. Remember, rising air expands and cools adiabatically if the air is moist enough and rises high enough to cool to its dew point. Water vapor condenses onto condensation nuclei, forming countless tiny droplets suspended in the air. These droplets scatter sunlight in all directions, making clouds appear white when they are thin and gray, or dark when they are thick and full of water. Clouds come in many forms, each telling a story about the atmospheric conditions that created it. Meteorologists classify clouds based on their altitude and shape. High clouds, above about 6,000 meters, include cirrus, cirrostratus, and cirrocumulus. Cirrus clouds are thin, wispy, and made of ice crystals. They often appear as delicate streaks or feathers across the sky, and typically indicate fair weather, though they may signal an approaching warm front. Cirrostratus clouds form thin sheets that can cover the entire sky, creating a milky or hazy appearance. They often produce halos around the sun or moon. Cirrocumulus clouds appear as small, white patches or ripples, sometimes called a mackerel sky. Middle-level clouds between about 2,000 and 6,000 meters include altocumulus and altostratus. Altocumulus clouds form layers or patches of gray or white clouds, often with a rippled or rolling appearance. They usually indicate fair weather but can precede thunderstorms. Altostratus clouds create gray or blue-gray sheets that often cover the sky. The sun may be visible through them as a dim disk. These clouds often form ahead of storms with continuous rain or snow. Low clouds below about 2,000 meters include stratus, stratocumulus, and nimbostratus. Stratus clouds are uniform gray layers that often produce drizzle or light snow. They can create overcast days and may reduce visibility. Stratocumulus clouds form low, lumpy layers, often appearing as a gray blanket with some breaks. They rarely produce significant precipitation. Nimbostratus clouds are dark gray, shapeless layers that produce steady rain or snow. They often accompany warm fronts. Clouds with significant vertical development, extending through multiple levels, include cumulus and cumulonimbus. Cumulus clouds are the puffy cotton ball clouds often seen on pleasant days. They form when pockets of warm air rise, cool, condense, and then stop rising because they are no longer warmer than the surrounding air. Fair weather cumulus clouds indicate instability but are harmless. However, if conditions are right, cumulus clouds can grow into towering cumulus and eventually into cumulonimbus, the thunderstorm clouds. Cumulonimbus clouds are the giants of the sky, sometimes reaching heights of 15,000 meters or more. They have a characteristic anvil-shaped top, formed when rising air hits the stable stratosphere and spreads horizontally. These clouds produce heavy rain, lightning, thunder, hail, strong winds, and sometimes tornadoes. They represent the atmosphere's most intense vertical circulation and embody the power of convection. Humidity measures the amount of water vapor in the air, but it can be expressed in different ways. Absolute humidity is the actual mass of water vapor per unit volume of air. Specific humidity is the mass of water vapor per unit mass of air. Most commonly, we hear about relative humidity, which compares the amount of water vapor in the air to the maximum amount the air could hold at that temperature, expressed as a percentage. A relative humidity of 50% means the air contains half as much water vapor as it could hold at that temperature. If the temperature rises without adding moisture, relative humidity decreases because warm air can hold more water. If the temperature falls, relative humidity increases, even though the actual amount of water vapor has not changed. This is why mornings often feel more humid than afternoons on days when no weather system is moving through. The air cools overnight, raising the relative humidity, and may even reach 100%, forming dew on grass and surfaces. Fog is simply a cloud that forms at ground level. It occurs when air near the surface cools to its dew point. Different types of fog form under different conditions. Radiation fog forms on clear, calm nights when the ground loses heat through radiation, cooling the air immediately above it. This type of fog is common in valleys and low-lying areas, and typically dissipates after sunrise as the ground warms. Advection fog forms when warm, moist air moves over a cooler surface, cooling to its dew point. This is common in coastal areas where warm ocean air moves over cold coastal waters. San Francisco's famous fog is an example of advection fog. Upslope fog occurs when air is forced to rise over mountains and cools adiabatically to its dew point. Water's journey through the atmosphere is continuous. It evaporates from the surface, rises as invisible vapor, condenses into visible clouds, and eventually returns to the surface as precipitation. This cycle, the water cycle or hydrologic cycle, is fundamental to weather and climate. It redistributes heat around the planet because when water evaporates, it absorbs heat energy, and when it condenses, it releases that heat energy back to the atmosphere. This latent heat release is what powers tropical storms and is a major energy source for many weather systems. Wind, the invisible sculptor. Wind is air in motion, and it is both cause and effect in weather. Temperature and pressure differences cause wind, and wind in turn transports heat and moisture, creating new weather patterns. Wind can be gentle, a light breeze barely rustling leaves, or violent hurricane-force gusts capable of destroying buildings. Understanding wind means understanding the forces that move the atmosphere. At its most basic, wind flows from high pressure to low pressure. If Earth did not rotate, wind would blow directly from highs to lows, taking the shortest path. But because Earth spins, the Coriolis effect deflects moving air to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection, combined with the pressure gradient force, the push from high to low pressure, causes wind to spiral around pressure systems rather than flowing straight into or out of them. There is also friction, especially near the surface. When wind blows over land or water, friction with the surface slows it down. This friction is greater over rough terrain, forests, and cities than over smooth surfaces like oceans or ice. Near the surface, friction disrupts the balance between the pressure gradient force and the Coriolis effect, causing wind to flow slightly inward toward low-pressure systems and slightly outward from high-pressure systems. Above about 1 kilometer, friction becomes negligible, and winds flow more smoothly around pressure systems, a level called the gradient wind level. The combination of pressure gradient, Coriolis effect, and friction creates the winds we experience daily. But there are also global-scale wind patterns, predictable flows that result from the planet's heat distribution and rotation. The trade winds blow steadily from the subtropical highs toward the equator, providing reliable winds that sailors have used for centuries. The westerlies dominate the middle latitudes, blowing generally from west to east, which is why weather systems in North America and Europe typically move from west to east. Embedded in the westerlies is the jet stream, a narrow band of very strong winds at high altitudes, typically between 9 and 12 kilometers up, where the troposphere meets the stratosphere. Jet streams form where there are large temperature differences between air masses, particularly along the boundary between cold polar air and warm tropical air. These winds can exceed 300 kilometers per hour and play a crucial role in steering weather systems. The polar jet stream meanders around the middle latitudes, sometimes pushing far south, bringing cold Arctic air with it, and sometimes retreating north, allowing warm air to surge poleward. Its position and strength vary with the seasons and with longer-term climate patterns. When the jet stream dips south in winter, it brings cold waves and winter storms. When it bulges north in summer, it allows heat waves. Weather forecasters closely monitor the jet stream because its behavior determines much of the weather experienced in the middle latitudes. There is also a subtropical jet stream at lower latitudes, and in winter, the two jet streams can interact, influencing storm development. Hurricanes and tropical storms generally stay away from the jet stream because its strong winds and wind shear disrupt their organization. But when a hurricane moves north and encounters the jet stream, the jet can accelerate its forward motion and sometimes enhance its rainfall. Local winds are created by local temperature and pressure differences. Sea breezes and land breezes result from differential heating of land and water. During the day, land heats up faster than water, creating lower pressure over land and higher pressure over water. Air flows from the water toward the land, creating a sea breeze. At night, land cools faster than water, reversing the pressure gradient and creating a land breeze from land to sea. These breezes can bring relief from hot temperatures and affect coastal weather. Mountain and valley winds follow a similar pattern. During the day, mountain slopes heat up, warming the air adjacent to them. This air rises up the slopes, creating valley winds. At night, the slopes cool, and dense, cold air drains down into the valleys, creating mountain winds. In deep valleys, this cold air can pool, creating very cold temperatures and frost even in otherwise mild conditions. Chinook winds, also called Foe-Han winds, occur when air is forced over a mountain range. As the air rises on the windward side, it cools and may lose moisture as precipitation. After crossing the ridge, the now drier air descends the leeward side, compressing and warming rapidly. By the time it reaches the valley floor, it can be much warmer than it was before starting its journey over the mountains. Chinook winds can raise temperatures dramatically in just a few hours, melting snow and creating spring-like conditions in the middle of winter. Katabatic winds are downslope winds driven by gravity. In places like Antarctica and Greenland, cold, dense air forms over high ice plateaus and then flows downhill, sometimes reaching hurricane strength. These winds can be sustained and fierce, making some of the coldest inhabited places on Earth even more inhospitable. Wind also plays a vital role in distributing heat and moisture around the planet. Warm winds bring warmth, and cold winds bring cold. Dry winds desiccate, and moist winds bring humidity and often precipitation. Prevailing winds determine regional climates. For example, the west coast of North America receives moisture-laden winds from the Pacific Ocean, bringing heavy rainfall to coastal regions. The interior of continents, far from ocean moisture sources and often sheltered by mountains, tend to be drier. Wind speed is measured in various units, including miles per hour, kilometers per hour, knots, and meters per second. The Beaufort scale, developed in the early 1800s, classifies wind by its observable effects, from calm 0 on the scale, where smoke rises vertically, to hurricane force 12 on the scale, where devastation occurs. Weather forecasters use anemometers to measure wind speed and wind vanes to measure wind direction, with direction defined as where the wind is coming from, not where it is going. Wind shapes our experience of weather. A cold day feels much colder when wind blows because wind accelerates the transfer of heat from our bodies to the air, a phenomenon called wind chill. A hot day can feel more pleasant with a breeze, as moving air evaporates perspiration and cools the skin. Wind also determines wave height on oceans and lakes, affects fire spread, influences air quality by dispersing or concentrating pollutants, and guides migrating birds and insects. Precipitation in all its forms. Clouds may form when air rises and cools to its dew point, but the tiny droplets that make up clouds are so small and light that they remain suspended in the air, kept aloft by gentle updrafts. For precipitation to occur, these droplets must grow large enough to overcome updrafts and fall to the ground. This happens through two primary mechanisms. In warm clouds, where temperatures are above freezing throughout, droplets grow by collision and coalescence. Larger droplets fall faster than smaller ones, and as they fall, they collide with smaller droplets in their path, merging into progressively larger drops. Once a droplet grows to about 1/10 of a millimeter in diameter, it falls as drizzle. If it continues growing and reaches about 1/2 millimeter or larger, it becomes rain. The largest raindrops are about 5 millimeters in diameter. Drops larger than this break apart as they fall through the air. In cold clouds, where temperatures are below freezing at least at higher altitudes, a different process dominates. These clouds contain both supercooled water droplets, liquid water that remains liquid even below 0 degrees Celsius, and ice crystals. Ice crystals can grow by deposition, water vapor changing directly from gas to solid without passing through the liquid phase. In a mixed phase cloud, ice crystals grow faster than droplets because the saturation vapor pressure over ice is lower than over liquid water. This means water vapor preferentially deposits onto ice crystals, and supercooled droplets evaporate, their moisture transferring to the ice crystals. This process, called the Bergeron-Fine-Dyson process, is efficient at producing precipitation in mid-latitude and polar regions. As ice crystals grow and become heavy, they begin to fall. As they descend through warmer layers of the atmosphere, they may melt, turning into raindrops. If they reach the ground before melting completely, they fall as snow. Snow forms when ice crystals in clouds stick together, creating snowflakes. The shape and size of snowflakes depend on temperature and humidity. At temperatures just below freezing, sticky, wet snow falls in large, clumping flakes. At very cold temperatures, snow is dry and powdery, with smaller, more distinct crystals. The classic six-pointed snowflake shape arises from the hexagonal structure of ice crystals. As water molecules freeze, they arrange themselves in a hexagonal lattice, and as the crystal grows, it develops 6 branches. The intricate patterns within each snowflake result from the crystal's journey through the cloud, experiencing varying temperatures and humidity levels. Each snowflake's path is unique, so each snowflake has a unique structure. While it is said that no two snowflakes are exactly alike, this refers to large, complex snowflakes. Simple ice crystals in very cold conditions can be quite similar. Sleet forms differently. It begins as snow high in the atmosphere, but as it falls through a layer of warm air above freezing, it melts into raindrops. If these drops then pass through a thick layer of sub-freezing air near the surface, they refreeze into small ice pellets before hitting the ground. These pellets bounce when they strike surfaces and accumulate like tiny hailstones. Sleet is different from freezing rain, which also starts as snow, melts into rain, but then does not refreeze before reaching the ground. Instead, freezing rain falls as supercooled liquid that instantly freezes upon contact with surfaces that are below 0 degrees Celsius, coating everything in smooth, hazardous ice. Ice storms, which occur when significant amounts of freezing rain fall, can be beautiful but destructive. The weight of ice on trees and power lines can snap branches and bring down electrical infrastructure, causing widespread power outages. Roads become dangerously slick, and even walking becomes hazardous. Ice storms typically occur when a warm front rides over a shallow layer of cold air trapped at the surface, a common situation in winter. Hail is another form of frozen precipitation, but unlike sleet or snow, hail forms in strong thunderstorms with powerful updrafts. Hailstones begin as ice pellets or frozen raindrops. In a severe thunderstorm, strong updrafts, sometimes exceeding 100 kilometers per hour, carry these pellets upward into the freezing levels of the cloud. As the pellet travels through the cloud, supercooled water droplets collide with it and freeze, adding layers of ice. The pellet may be carried up and down multiple times, each trip adding more ice until it becomes too heavy for the updraft to support, and it falls to the ground. Cutting a hailstone in half reveals concentric layers, like an onion, each layer representing a journey through different parts of the storm cloud. Small hail, pea-sized or marble-sized, is common in many thunderstorms. Large hail, golf ball-sized or even softball-sized, occurs in the most severe storms, supercells, and can cause significant damage to crops, vehicles, and buildings. The largest hailstone ever recorded in the United States fell in South Dakota in 2010, measuring 20 centimeters in diameter and weighing nearly a kilogram. Rainfall intensity varies widely. Light rain or drizzle produces less than 2.5 millimeters per hour. Moderate rain produces between 2.5 and 10 millimeters per hour. Heavy rain produces between 10 and 50 millimeters per hour. Very heavy rain, often associated with thunderstorms, can exceed 50 millimeters per hour. In extreme cases, tropical storms and hurricanes can produce rainfall rates over 100 millimeters per hour, leading to catastrophic flooding. Precipitation is measured with rain gauges, simple devices that collect and measure rainfall. The measurement is given as depth, the depth of water that would accumulate on a flat surface if none ran off or evaporated. Snow is often measured both as depth and as snow water equivalent, the amount of water contained in the snow. On average, 10 centimeters of snow contains about 1 centimeter of water, but this ratio varies. Wet, heavy snow has a higher water content, while light, fluffy snow has a lower water content. Different regions receive vastly different amounts of precipitation. Some places, like Mount Waialeale in Hawaii, receive over 10 meters of rain annually, making them among the wettest places on Earth. Others, like parts of the Atacama Desert in Chile, receive less than a millimeter per year and can go years without measurable rain. These differences result from atmospheric circulation patterns, proximity to moisture sources, topography, and prevailing winds. Weather fronts and air masses. Air masses are large bodies of air, often thousands of kilometers across, that have relatively uniform temperature and humidity characteristics. They form when air sits over a large region for an extended period, taking on the properties of the surface below. Air masses are classified by their source region, with Arctic and polar air masses being cold, tropical air masses being warm, maritime air masses being moist, and continental air masses being dry. A continental polar air mass, for example, forms over the cold land surfaces of northern Canada or Siberia, and it is cold and dry. A maritime tropical air mass forms over warm ocean waters, like the Gulf of Mexico or the tropical Atlantic, and it is warm and humid. When air masses move away from their source regions, they carry their temperature and moisture characteristics with them, bringing changes in weather. The boundary between two different air masses is called a front. Fronts are zones of transition where temperature, humidity, wind, and pressure change relatively rapidly over short distances. There are four main types of fronts: cold fronts, warm fronts, stationary fronts, and occluded fronts. A cold front occurs when a cold air mass advances and pushes under a warmer air mass. Cold air is denser than warm air, so the cold air acts like a wedge, lifting the warm air. This lifting is often steep and rapid. If the warm air is moist and unstable, vigorous convection occurs, producing a line of towering cumulus and cumulonimbus clouds along the front. These clouds bring heavy showers, thunderstorms, strong gusty winds, and sometimes hail or tornadoes. The passage of a cold front is usually marked by a sudden wind shift, a drop in temperature, rising pressure, and clearing skies behind the front as drier air moves in. In summer, cold fronts often trigger severe thunderstorms. In winter, they bring snow showers and a sharp, cold snap. A warm front occurs when a warm air mass advances and slides over a retreating cold air mass. Because warm air is less dense, it rises gently over the cold air, creating a gradual slope. This gentle lifting produces stratiform clouds, layered clouds that cover large areas. Ahead of a warm front, high cirrus clouds appear first, sometimes a day or more before the front arrives. As the front approaches, the clouds lower and thicken, progressing through cirrostratus, altostratus, and finally nimbostratus, which produces steady, continuous precipitation. The precipitation can extend hundreds of kilometers ahead of the surface front. When the warm front passes, temperatures rise, winds shift, and skies may gradually clear or remain partly cloudy. Warm fronts move more slowly than cold fronts and produce less intense but more prolonged weather. A stationary front occurs when a cold and warm air mass meet, but neither advances. The front barely moves, and weather conditions near the front can persist for several days. Clouds and precipitation, similar to those of a warm front, form along and north of the stationary front. The weather is often cloudy and wet for extended periods. An occluded front forms during the later stages of a mid-latitude cyclone's life cycle. Cold fronts typically move faster than warm fronts. When a cold front catches up to a warm front, the warm air is lifted entirely off the surface, and the two cold air masses meet. The type of occlusion depends on the relative temperatures of the cold air masses. In a cold occlusion, the air behind the cold front is colder than the air ahead of the warm front. In a warm occlusion, the air ahead of the warm front is colder. Occluded fronts produce complex weather patterns, often with widespread clouds and precipitation. These frontal systems are the primary weather makers in the middle latitudes. The clash between cold polar air and warm tropical air creates a battleground for storms, and the jet stream, which often flows above these frontal boundaries, helps steer and intensify these systems. A typical mid-latitude cyclone begins as a wave along a frontal boundary, a kink where the front begins to curve. Low pressure develops at this kink, drawing in air. Warm air advances northward on the east side of the low, forming the warm front. Cold air pushes southward on the west side, forming the cold front. Between the two fronts lies a warm sector, a region of warm, often humid air. As the cyclone develops, the cold front rotates around the low-pressure center, eventually catching the warm front and lifting the warm sector off the ground, creating an occlusion. The storm reaches peak intensity shortly before or during occlusion, then begins to weaken as the temperature contrasts diminish. This entire process, from initial wave to dissipation, typically takes several days and transports vast amounts of heat, moisture, and energy across the middle latitudes. These cyclones bring the changeability characteristic of mid-latitude weather. A warm, humid day can give way to thunderstorms as a cold front passes, followed by cool, clear conditions. A few days later, another system approaches, bringing clouds and rain with a warm front, then warming up behind it, only to have the cycle repeat. This constant procession of high and low pressure systems, fronts, and air masses is the pulse of weather in places like North America, Europe, and parts of Asia. Understanding fronts helps us anticipate weather changes. When a cold front approaches, we can expect a line of storms, a temperature drop, and improving conditions afterward. When a warm front approaches, we prepare for prolonged clouds and rain, followed by warmer temperatures. Meteorologists track fronts on weather maps, using blue lines with triangles for cold fronts, red lines with semicircles for warm fronts, and alternating red and blue for stationary and occluded fronts. Storms, nature's power unleashed. Thunderstorms are among the most common and most dramatic weather phenomena. At any given moment, about 2,000 thunderstorms are occurring somewhere on Earth. While most are benign, producing brief heavy rain and perhaps a few flashes of lightning, some grow into powerful engines of destruction. A thunderstorm forms when three ingredients come together: moisture, instability, and a lifting mechanism. Moisture provides the fuel in the form of water vapor that condenses, releasing latent heat to power the storm. Instability means that the atmosphere is prone to convection, with warm, buoyant air at the surface and cooler air aloft. The lifting mechanism can be heating of the ground, a cold front, a sea breeze, or flow over mountains. Anything that forces air upward to start the process. A single-cell thunderstorm, also called an ordinary or air mass thunderstorm, is the simplest type. It goes through three stages. The cumulus stage begins when moist air rises, cools, and condenses, forming a growing cumulus cloud. Updrafts dominate, and the cloud builds vertically. After about 10 to 15 minutes, the cloud reaches the mature stage. Precipitation begins to fall, creating downdrafts alongside the still active updrafts. This is when the storm is most intense, producing heavy rain, frequent lightning, and sometimes small hail. The mature stage lasts 15 to 30 minutes. Eventually, the downdrafts spread throughout the storm, cutting off the updraft, and the storm enters the dissipating stage. Rain lightens, the cloud loses its towering structure, and the storm dissipates, usually within an hour of forming. More complex are multi-cell thunderstorms, clusters of cells at various stages of development. As one cell matures and begins to dissipate, its downdraft spreads out along the ground as a gust front, a boundary of cool outflow air. This gust front can lift warm, moist air ahead of it, triggering new cells. The result is a cluster of storms that can last several hours, moving across the landscape and producing repeated rounds of heavy rain, lightning, and gusty winds. The most powerful thunderstorms are supercells, long-lived rotating storms that can produce the most severe weather, including large hail, damaging winds, flash floods, and violent tornadoes. Supercells are relatively rare, accounting for only a small fraction of all thunderstorms, but they are responsible for a disproportionate amount of severe weather damage. A supercell requires strong wind shear, a change in wind speed or direction with altitude. This wind shear causes the updraft to rotate, creating a mesocyclone, a rotating column of air within the storm. The rotation organizes the storm, allowing it to sustain itself for hours. The mesocyclone can be several kilometers in diameter, and from it, tornadoes sometimes descend. Lightning is one of the most visible aspects of thunderstorms, and one of the most misunderstood. Lightning is a massive electrical discharge that occurs because thunderstorms are enormous electrical generators. Within a storm cloud, collisions between ice particles, water droplets, and hailstones separate electrical charges. Typically, positive charges accumulate near the top of the cloud, and negative charges concentrate near the middle and lower parts. The ground below often becomes positively charged by induction. When the electrical potential between the cloud and the ground, or between different parts of the cloud, becomes large enough, the air's insulating properties break down, and a lightning bolt surges, equalizing the charge. Most lightning occurs within clouds or between clouds, but cloud-to-ground lightning is what we notice and what poses the greatest danger. A lightning bolt can carry over 100 million volts and heat the air along its path to about 30,000 degrees Celsius, 5 times hotter than the surface of the sun. This intense heating causes the air to expand explosively, creating the shock wave we hear as thunder. Because light travels much faster than sound, we see lightning before we hear thunder. By counting the seconds between the flash and the rumble and dividing by 3, we can estimate the distance to the lightning in kilometers. If you see lightning and hear thunder within a few seconds, you are close to the storm and should seek shelter immediately. Lightning can strike several kilometers from a thunderstorm, so if you can hear thunder, you are within striking distance. Thunderstorms can also produce intense straight-line winds called downbursts. A downburst occurs when a strong downdraft from a storm hits the ground and spreads out radially. Microbursts, downbursts less than 4 kilometers across, are particularly dangerous to aircraft during takeoff and landing because they create strong wind shear. Larger downbursts, called macrobursts, can produce damaging winds over areas tens of kilometers across. A derecho is a widespread, long-lived windstorm associated with a line of severe thunderstorms. Derechos produce damaging straight-line winds over areas hundreds of kilometers long and more than 100 kilometers wide. Wind gusts in derechos can exceed 160 kilometers per hour, rivaling tornadoes. Derechos typically form from bow echoes, curved lines of thunderstorms that bow outward as strong downdrafts push the gust front forward. Flash floods are another deadly thunderstorm hazard. When thunderstorms move slowly or repeatedly pass over the same area, rainfall accumulates rapidly, overwhelming drainage systems and causing streams and rivers to rise quickly. Flash floods can occur within minutes, catching people in vehicles or on foot. More people die from floods than from any other thunderstorm-related hazard. Meteorologists issue watches and warnings for severe thunderstorms. A watch means conditions are favorable for severe weather to develop. A warning means severe weather has been observed or detected on radar and is imminent or occurring. Taking shelter when warnings are issued is crucial for safety. Tornadoes. The vortex tornadoes are among the most violent and feared weather phenomena. A tornado is a rapidly rotating column of air extending from the base of a thunderstorm to the ground. Most tornadoes are less than 100 meters wide and last only a few minutes, but the strongest can be more than 3 kilometers wide and stay on the ground for hours, carving paths of devastation exceeding 100 kilometers. Tornadoes form in environments with strong wind shear and instability, conditions most often found in supercell thunderstorms. The exact process of tornado formation, tornadogenesis, is still not fully understood, but it generally begins with the mesocyclone, the rotating updraft in a supercell. For a tornado to form, this rotation must extend downward to the ground. Several factors contribute, including the downdraft, the rear flank downdraft wrapping around the mesocyclone, temperature differences, and localized intensification of rotation. When a tornado touches down, it becomes a narrow, intense vortex with winds that can exceed 400 kilometers per hour in the strongest tornadoes. The enhanced Fujita scale, which replaced the original Fujita scale, rates tornadoes from EF0 to EF5 based on the damage they cause. EF0 tornadoes have estimated wind speeds of 105 to 137 kilometers per hour and cause light damage. EF5 tornadoes have estimated wind speeds exceeding 322 kilometers per hour and cause incredible damage, leveling well-built homes and hurling cars like missiles. Most tornadoes in the United States occur in an area known as Tornado Alley, stretching from Texas northward through Oklahoma, Kansas, Nebraska, and South Dakota. This region experiences frequent, severe thunderstorms during spring and early summer, when warm, moist air from the Gulf of Mexico clashes with cool, dry air from Canada, and strong wind shear aloft provides the necessary conditions for supercells. However, tornadoes can occur almost anywhere in the United States and around the world. The southern United States experiences a secondary tornado season in late fall and winter, when strong cold fronts and low pressure systems create favorable conditions. Tornadoes also occur in other countries including Canada, parts of Europe, Argentina, South Africa, Australia, and Bangladesh. tornado appearance varies. Some are thin, rope-like funnels. Others are wide, wedge-shaped columns obscured by rain and debris. The visible funnel is not the wind itself, but condensed water droplets and dust and debris sucked up from the ground. Sometimes, especially at night or when wrapped in rain, tornadoes are invisible until they strike. The danger from tornadoes comes not only from the wind, but from the debris it carries. Flying boards, shattered glass, and twisted metal become deadly projectiles. Even in relatively weak tornadoes, debris can cause serious injury. In strong tornadoes, entire structures disintegrate, and the landscape is scoured clean. Tornado warnings are issued when a tornado has been sighted or indicated by radar. Doppler radar can detect rotation within thunderstorms, and meteorologists look for signatures like hook echoes, curved appendages on the radar reflectivity indicating the presence of a mesocyclone, and debris balls, bright spots indicating debris lofted into the air. When a warning is issued, people in the path should seek shelter immediately in a basement or an interior room on the lowest floor, away from windows. Tornado safety has improved dramatically with better warnings and public awareness, but tornadoes remain dangerous. The most violent tornadoes can cause catastrophic damage, and even with warning, options for protection are limited if you are caught in the open. Understanding tornado formation, recognizing the conditions that favor them, and heeding warnings are the best defenses. Hurricanes, oceanic giants. Hurricanes, also called typhoons or tropical cyclones, depending on their location, are the largest and most powerful storms on Earth. These massive, rotating storms form over warm tropical oceans and are fueled by the energy released when water vapor condenses. While tornadoes are small and short-lived, hurricanes can be hundreds of kilometers in diameter and last for weeks, traveling thousands of kilometers across ocean and land. A hurricane begins as a tropical disturbance, a cluster of thunderstorms over tropical waters. When conditions are favorable, the disturbance can organize and intensify. For a hurricane to form, several conditions must be met. Ocean water must be at least 26.5 degrees Celsius to a depth of about 50 meters, providing the warm, moist air needed for fuel. The atmosphere must be unstable, allowing convection. There must be low wind shear because strong winds at different altitudes would disrupt the storm's organization. The disturbance must be at least about 5 degrees latitude from the equator, so the Coriolis effect can organize rotation. Hurricanes do not form at the equator because the Coriolis effect is zero there. When a tropical disturbance intensifies, thunderstorms begin to organize around a center. If sustained winds reach 63 kilometers per hour, the system is classified as a tropical storm and is given a name. As the storm continues to intensify, the central pressure drops and winds increase. When sustained winds reach 119 kilometers per hour, the system becomes a hurricane. Hurricanes are classified by intensity using the Saffir-Simpson scale, based on sustained wind speed. Category 1 hurricanes have winds of 119 to 153 kilometers per hour and cause some damage. Category 5 hurricanes have winds exceeding 252 kilometers per hour and cause catastrophic damage. The categories help communicate the storm's potential, though damage depends not only on wind speed, but also on storm surge, rainfall, and the vulnerability of affected areas. The structure of a mature hurricane is distinctive. At the center is the eye, a region of calm winds, clear skies, and low pressure, typically 20 to 60 kilometers in diameter. Surrounding the eye is the eye wall, a ring of the most intense thunderstorms with the strongest winds and heaviest rainfall. Outside the eye wall, rain bands spiral outward, curved bands of thunderstorms separated by areas of lighter rain. The eye forms because air spiraling inward cannot reach the center due to the storm's rotation. Instead, it rises in the eye wall. The updraft so intense it punches through the tropopause. At high altitude, the air flows outward, then sinks gently in the center, creating the calm eye. People in the eye might experience a surreal calm, with blue skies overhead. But they are in the most dangerous part of the storm, about to be hit by the opposite side of the eye wall as the storm passes. Hurricanes derive their energy from warm ocean water. As air spirals inward toward the low-pressure center, it picks up moisture evaporating from the warm sea surface. This moist air rises in the eye wall, and as the moisture condenses into rain, it releases latent heat. This heat warms the air, making it more buoyant, strengthening the updraft, lowering the central pressure further, and increasing the winds. This is a positive feedback loop. As long as the storm remains over warm water, it can maintain or even intensify. When a hurricane moves over cooler water or makes landfall, it loses its energy source. Without warm water to evaporate and provide moisture, the storm weakens. Increased friction over land also disrupts the circulation. Most hurricanes weaken rapidly once they make a landfall, but they can still produce heavy rain and flooding well inland before dissipating or transitioning into extratropical cyclones. The greatest threat from hurricanes is often not the wind but the storm surge. Storm surge is an abnormal rise in sea level caused by the hurricane's winds pushing water toward the coast. In a powerful hurricane, storm surge can exceed 6 meters, inundating coastal areas and causing catastrophic flooding. When storm surge coincides with high tide, the flooding is even worse. Storm surge has caused most of the hurricane-related deaths throughout history. Hurricanes also produce heavy rainfall, sometimes exceeding 50 centimeters over a few days. This rainfall causes inland flooding, which can be devastating and long-lasting. Some of the deadliest hurricanes in history have caused their greatest damage through rainfall flooding, not wind or surge. Tornadoes often form in the outer rain bands of hurricanes, especially in the right front quadrant of the storm, relative to its motion. These tornadoes are usually weak, but they add another hazard to an already dangerous situation. Hurricane forecasting has improved significantly. Satellites monitor tropical disturbances and developing storms. Computer models simulate storm tracks, though predicting intensity remains challenging. Hurricane hunters, aircraft that fly into storms, gather data on wind speed, pressure, and structure. When a hurricane threatens land, forecasts provide days of warning, allowing evacuations and preparations. However, the exact path and intensity can change, and overwarning can lead to complacency, while underwarning can be disastrous. Hurricanes are a natural part of Earth's climate system. They transport heat from the tropics toward the poles, helping balance the planet's energy. But when they strike populated coasts, they cause immense destruction. Understanding hurricanes, respecting their power, and heeding warnings are essential for safety. Winter weather phenomena. Winter brings its own set of weather challenges, transforming landscapes with snow and ice, and creating hazards that differ markedly from summer storms. While thunderstorms and tornadoes are warm season phenomena, winter storms dominate the cold months, bringing heavy snowfall, ice, and bitter cold. A blizzard is defined not just by heavy snow but by strong winds and reduced visibility. In the United States, a blizzard requires sustained winds or frequent gusts exceeding 56 kilometers per hour, considerable falling or blowing snow, and visibility reduced to less than 400 meters for at least 3 hours. Blizzards can occur without heavy snowfall if strong winds lift existing snow off the ground, a phenomenon called a ground blizzard. Blizzards form when strong low-pressure systems draw in cold Arctic air, which then picks up moisture, often from large bodies of water or from atmospheric rivers of moisture. The intense pressure gradient between the low and surrounding highs produces strong winds. If temperatures are cold enough, precipitation falls as snow, and the wind blows it horizontally, creating whiteout conditions where it is impossible to see more than a few meters. Being caught in a blizzard is dangerous. Visibility can drop to zero, making it easy to become disoriented even in familiar surroundings. Wind chill, the combined effect of cold air and wind, can lead to frostbite and hypothermia in minutes. Blizzards can paralyze regions, closing roads, downing power lines, and trapping people in homes or vehicles. Lake effect snow is a localized phenomenon that occurs downwind of large lakes, most notably the Great Lakes in North America. When cold Arctic air moves across the relatively warm lake water, the air picks up moisture and heat from the lake surface. This moist, warmed air becomes buoyant and rises, forming clouds and snow showers downwind. Lake effect snow can be intense, producing snowfall rates exceeding 5 centimeters per hour and accumulations exceeding a meter in narrow bands. Areas just a few kilometers apart can experience vastly different snowfall amounts, with heavy snow in the snowbelt and little to no snow outside it. Ice storms caused by freezing rain coat everything in a glaze of ice. These storms occur when precipitation falls through a warm layer aloft, melting into rain, then enters a sub-freezing layer near the surface but does not refreeze before reaching the ground. The supercooled raindrops freeze on contact with cold surfaces, building up layers of ice. Even a few millimeters of ice can snap tree branches and power lines, causing widespread outages that can last for days or weeks in severe cases. Ice storms make travel nearly impossible as roads become skating rinks. Nor'easters are powerful storms that affect the east coast of North America, typically in winter. The name comes from the strong northeasterly winds along the coast ahead of the storm. Nor'easters form when a low-pressure system intensifies off the Atlantic coast, drawing in cold air from the north and moisture from the Atlantic. These storms can produce heavy snow, rain, high winds, coastal flooding, and beach erosion. They can be as large and powerful as hurricanes, but thrive in cold conditions. Extreme cold outbreaks, also called cold waves or Arctic outbreaks, occur when the jet stream dips far southward, allowing bitterly cold Arctic air to plunge into lower latitudes. These events can bring temperatures far below normal, sometimes for extended periods. The cold itself is dangerous, but combined with wind, the wind chill can make it feel even colder, increasing the risk of frostbite and hypothermia. Extreme cold can also stress infrastructure, causing pipes to freeze and burst, and increasing energy demand for heating. Winter weather advisories, watches, and warnings inform the public of impending winter storms. An advisory means winter weather is expected that will cause inconvenience, but not necessarily dangerous conditions. A watch means conditions are favorable for significant winter weather. A warning means significant winter weather is occurring or imminent. Staying informed and prepared is crucial during winter months, especially in regions prone to severe winter weather. Weather prediction and technology. Predicting the weather is an ancient human endeavor. For thousands of years, people observed the sky, felt the wind, and watched animal behavior, developing folklore and rules of thumb to anticipate changes. Some of this folk wisdom has merit. Red sky at night, sailors' delight. Red sky in morning, sailors take warning, is based on the observation that weather systems generally move from west to east, and red skies are caused by sunlight filtering through clouds. But reliable weather prediction requires more than observation. It requires understanding the underlying physics and mathematics of the atmosphere. The scientific study of weather began in earnest in the 17th and 18th centuries with the invention of instruments like the barometer, thermometer, and anemometer. These tools allowed quantitative measurements of atmospheric conditions. In the 19th century, the telegraph enabled observations from distant locations to be collected and synthesized, allowing meteorologists to create weather maps and track storms. A breakthrough came in the early 20th century when Lewis Fry Richardson proposed using mathematical equations to predict weather. The atmosphere obeys the laws of physics, specifically the equations of fluid dynamics and thermodynamics. If you know the current state of the atmosphere and solve these equations forward in time, you should be able to predict future conditions. Richardson attempted this manually, a heroic effort requiring countless calculations. His forecast took weeks to produce and was not accurate, but he demonstrated the concept. The advent of computers in the mid-20th century made numerical weather prediction feasible. By the 1950s, the first computer-generated weather forecasts were being produced. Since then, the field has advanced enormously. Modern weather prediction relies on complex computer models that simulate the atmosphere's behavior. These models divide the atmosphere into a three-dimensional grid, with points spaced tens or hundreds of kilometers apart horizontally and at various levels vertically. At each grid point, The model calculates temperature, pressure, humidity, wind, and other variables. The equations of motion, conservation of energy, and moisture are solved at each time step, typically a few minutes, and the model steps forward, simulating the atmosphere's evolution. Initial conditions, the current state of the atmosphere, are crucial. Models need accurate data about temperature, pressure, wind, humidity, and other variables around the globe. This data comes from a vast network of observations: surface weather stations, weather balloons, ships, buoys, aircraft, and satellites. Satellites are especially important because they provide continuous global coverage, including over oceans and remote regions where surface observations are sparse. Weather balloons, carrying radiosondes, ascend through the atmosphere twice daily at hundreds of locations worldwide, measuring temperature, humidity, and pressure, and tracking winds as they drift. Aircraft report temperature and wind at cruise altitudes. Weather radar detects precipitation and, using Doppler technology, measures wind speeds within storms. All this data is fed into data assimilation systems that blend observations with model forecasts to create the best estimate of the current atmospheric state, which then serves as the starting point for the forecast. Even with excellent observations and powerful computers, weather forecasts are never perfect. The atmosphere is a chaotic system, and small errors in the initial conditions can grow over time. This is the essence of chaos theory, and the reason there is an inherent limit to weather predictability. For short-range forecasts, a few days ahead, models are generally quite accurate. For medium-range forecasts, about a week ahead, accuracy decreases but is still useful. Beyond about 2 weeks, deterministic forecasts become unreliable because tiny uncertainties amplify into large errors. To address this, meteorologists use ensemble forecasting, running the same model multiple times with slightly different initial conditions or using multiple different models. The spread among the ensemble members indicates forecast uncertainty. If all members predict similar weather, confidence is high. If they diverge widely, uncertainty is large. Ensemble forecasts provide probabilistic information, such as the chance of rain or the range of possible temperatures, which is more useful than a single deterministic forecast. Satellites have revolutionized meteorology. Geostationary satellites orbit at the same rate Earth rotates, remaining fixed over one spot, providing continuous monitoring of weather systems. Polar orbiting satellites pass over the poles, circling Earth and scanning the entire globe twice a day. Satellites measure visible and infrared radiation, giving information about cloud cover, cloud top temperatures, sea surface temperatures, water vapor, and even atmospheric winds. Satellites can detect developing hurricanes, monitor storm intensity, track wildfire smoke, and observe ice cover. Doppler radar is another critical tool. By measuring the frequency shift of radar echoes, Doppler radar determines whether precipitation is moving toward or away from the radar, revealing wind patterns within storms. This technology allows meteorologists to detect rotation within thunderstorms, providing warnings for tornadoes. Dual polarization radar sends both horizontal and vertical pulses, providing better estimates of precipitation type and intensity. Weather forecasting has become more accurate over the decades, saving countless lives and allowing better planning for agriculture, transportation, energy, and many other sectors. However, forecasts will always have limitations due to the chaotic nature of the atmosphere. The goal is to continue improving models, observations, and understanding to push the limits of predictability as far as possible. Climate patterns and weather. Weather and climate are related but distinct. Weather is the state of the atmosphere at a specific place and time. It is what you experience when you step outside. Climate is the average weather over long periods, typically 30 years or more. Climate describes what is expected, while weather is what actually happens. Large-scale climate patterns influence weather around the world. One of the most significant is the El Niño Southern Oscillation, or ENSO, a climate phenomenon involving fluctuating ocean temperatures in the equatorial Pacific. Under normal conditions, trade winds blow from east to west across the Pacific, pushing warm surface water westward. This allows cold, nutrient-rich water to upwell along the coast of South America, supporting rich fisheries. In the western Pacific, warm water accumulates, and rising air produces heavy rainfall. During an El Niño event, the trade winds weaken or even reverse. Warm water sloshes back eastward, suppressing upwelling off South America and shifting the region of heavy rainfall toward the central and eastern Pacific. This alters atmospheric circulation patterns, affecting weather worldwide. El Niño tends to bring wetter conditions to the southern United States, drier conditions to the Pacific Northwest, and can influence hurricane activity in the Atlantic. In the western Pacific and Indonesia, El Niño often brings drought, sometimes causing devastating impacts on agriculture. La Niña is the opposite phase, characterized by stronger than normal trade winds and cooler than normal water in the eastern Pacific. La Niña tends to bring drier conditions to the southern United States, wetter conditions to the Pacific Northwest, and can enhance Atlantic hurricane activity. ENSO cycles irregularly, with El Niño and La Niña events occurring every few years, each lasting several months to a year or more. Predicting ENSO and understanding its impacts helps forecasters anticipate seasonal weather patterns. Other climate patterns also influence weather. The North Atlantic Oscillation, or NAO, involves fluctuations in atmospheric pressure between the Icelandic low and the Azores high. The phase of the NAO affects winter weather in Europe and eastern North America. The Pacific Decadal Oscillation and the Arctic Oscillation are other long-term patterns that modulate weather across large regions. Seasons are, of course, the most familiar climate pattern. Earth's tilt on its axis, about 23.5 degrees, causes different parts of the planet to receive varying amounts of sunlight throughout the year. When the northern hemisphere tilts toward the sun, it experiences summer, with longer days, higher sun angles, and warmer temperatures. 6 months later, when the northern hemisphere tilts away from the sun, it experiences winter, with shorter days, lower sun angles, and colder temperatures. The southern hemisphere experiences the opposite seasons. The transition seasons, spring and autumn, occur when neither hemisphere is tilted significantly toward or away from the sun. These seasons are characterized by moderate temperatures and often volatile weather. As the temperature contrast between polar and tropical air is still strong, fueling storms. Climate change, the long-term alteration of temperature and weather patterns primarily due to human activities, is affecting weather in observable ways. The burning of fossil fuels releases greenhouse gases, particularly carbon dioxide, into the atmosphere. These gases trap heat, warming the planet. Global average temperatures have risen about 1 degree Celsius since the late 19th century, and this warming is altering weather patterns. A warmer atmosphere holds more moisture, about 7% more for every degree Celsius of warming. This means precipitation events can be more intense. Heavy rainfall and extreme precipitation events have become more frequent in many regions. Warm air also enhances evaporation, contributing to droughts in areas where precipitation does not increase. Heat waves, prolonged periods of excessive heat, have become more frequent, longer lasting, and more intense. The warmest years on record have all occurred in the past 2 decades. Extreme heat poses serious health risks, particularly to vulnerable populations. The impacts of climate change on tropical cyclones are complex and still being studied. Warmer ocean temperatures provide more energy, potentially leading to stronger hurricanes. However, changes in atmospheric circulation could affect where and how often hurricanes form. Evidence suggests that while the total number of hurricanes might not change dramatically, the proportion of intense hurricanes, Category 4 and 5, may increase. Tornadoes are more challenging to link directly to climate change because they occur at small scales and are influenced by many factors. Some studies suggest changes in the environment favorable for tornadoes, but detecting long-term trends is difficult due to changes in observation methods over time. Winter storms and extreme cold events continue to occur, even as the climate warms. A warmer atmosphere does not mean the end of winter. However, cold extremes have generally become less frequent, while warm extremes have increased. The science of attributing specific weather events to climate change, called event attribution, has advanced. Scientists use climate models to compare the likelihood of an event occurring in the current warmed world versus a hypothetical world without human-caused climate change. Studies have found that many extreme events, particularly heat waves and heavy precipitation, have become more likely or more intense due to climate change. Climate and weather are interconnected. Climate sets the stage, providing the average conditions, and weather performs the play, bringing day-to-day variability. Understanding both is essential for anticipating future conditions and adapting to changes. A gentle closing. As we slowly return from this journey through the atmosphere, let your mind settle back into the present moment. You have traveled through invisible oceans of air, witnessed the birth of clouds and storms, felt the power of wind and the delicate balance of temperature and pressure. Weather, that ever-changing presence above us, is not just physics and mathematics. It is the language Earth speaks to itself, a conversation between sun and surface, ocean and land, heat and cold. Every breath you take is part of the atmosphere we have explored tonight. The air filling your lungs has circled the globe, risen in thunderstorms, descended in high-pressure systems, and carried moisture from distant seas. You are connected to weather in the most intimate way, participating in these cycles with every breath. If tonight's exploration brought you peace or curiosity, I invite you to like this video and subscribe to Sleepy Science Society. Your support helps this channel grow, bringing quiet science to more people seeking both knowledge and calm. Perhaps you will share this with someone who finds comfort in understanding the world, or leave a thought in the comments below, a shared moment of connection through curiosity. But for now, simply rest. Let the science we have explored tonight drift into the background of your awareness like distant clouds. You have learned, you have wondered, and now you can let it all settle into sleep. The atmosphere continues its endless dance, indifferent to our presence yet sustaining all life. Tomorrow, you will wake to new weather, new conditions shaped by forces we now understand just a little better. Close your eyes if they are not already closed. Feel the gentle weight of the air around you, that slight pressure reminding you that you rest at the bottom of an ocean of atmosphere. Let your breathing slow further. Let tension drain away like rain soaking into thirsty earth. The sky has shared its secrets tonight, and you have listened. Good night, sleep well, and may your dreams be as peaceful as a clear, starlit sky after a storm has passed.